Hello, my name is Kevin McGrath. I'm the CTO at Spot, and today we're going to be talking about reducing infrastructure cost and complexity with Kubernetes. Specifically, we want to drive into how optimized and efficient we can be running Kubernetes in the cloud. To start off, we're going to talk about the anatomy of Kubernetes, and there's really two components to Kubernetes that we need to be concerned with right now. The first is the control plane. The control plane is where the master nodes run. They house the database, API server, and scheduler normally. This is where all the connections from outside of the Kubernetes cluster come into that need to manage what's happening, what needs to be scheduled, what needs to be configured within the cluster, any access rights, so forth and so on. That all happens in the control plane. This is the part of the cluster that has 1, 3, maybe 5 instances. It doesn't scale very large, but it's extremely important to running the entire cluster, which has all of the worker nodes in it. Now we'll talk about the data plane, which is the part that you see on the right. This has all of the nodes or VMs associated with it. And on these VMs are where all the pods are run. Now, pods in Kubernetes is what contains the containers. Containers are deployed within pods. Pods are what scale across nodes. Now, every single node has what's called a kubelet. The kubelet communicates with the control plane. It communicates with the master nodes. It tells the master what type of characteristics that the node has, how much memory, how much CPU. It tells it what type of storage, what type of network. This is the communication. This is the link between the two planes. Now, there's another part to this called services, where if you need to get data from outside of the cluster to come into the cluster, you need to configure what's called service or ingress controllers. Now, these can be custom load balancers that you can find in the open source community, or they can be load balancers that are provisioned by the cloud providers themselves. This is the external facing URL or IP address that's associated with a service or an entire cluster and allows traffic inbound to all of the different pods within the cluster itself running on top of the VMs. For this conversation today, we're really going to be focused on the data plane management, the scale of these worker nodes, the scale of the work that is done in the cluster. This is the side of the cluster that can go from 0 nodes to 1,000 nodes. And this is where the most cost and most efficiency loss that we normally see with Kubernetes can occur. And this is what we really try to focus on to drive more efficiency out of Kubernetes clusters that are hosted in the cloud. So when we talk about scaling, there are really 2 levels of scaling that we're talking about. There's the pod scaling, and then there's the infrastructure scaling. The pod scaling is the native scaling to Kubernetes. Kubernetes scales everything by pods. Multiple containers can run in a pod. A pod runs on a node. Any number of pods can run across any number of nodes. Now, Kubernetes doesn't care what nodes things run on, as long as those nodes have the requirements to run those pods. So Kubernetes by itself is going to schedule pods as long as it has infrastructure to do so. So with static infrastructure underneath, as pods come into the system, Kubernetes is going to take those pods, find the instances that match the characteristics of the pod that needs to run, and run the pod. Now, as these pods expand and contract, the infrastructure to be efficient should also expand and contract along with the pods. Now, there's a few caveats that happen when you're scaling pods and also need to scale infrastructure. We're going to talk about those. First, we're going to talk about horizontal pod autoscaling, what it means to take pods and replicate them out across the environment. So natively to Kubernetes, there's a thing called the horizontal pod autoscaler, or the HPA. It relies on the metric server. The metric server feeds HPA the metrics of what's happening with different pods in the environment. And then the HPA decides which deployments, consisting of which pods, need to scale up or scale down. The HPA will decide within limits that if it should schedule more pods or less pods. Now, what the HPA does not do is decide how much more infrastructure should be allocated or should be removed. It only cares about pods and scaling the number of pods to meet the request. The job of scaling the infrastructure is left to other scaling services. The second type of default scaling that's included with Kubernetes is vertical pod auto scaling. And VPA does the same thing. It checks the metric server, or metric server feeds VPA. And VPA will decide for a single pod whether that pod should use more memory, less memory, more CPU, or less CPU. Now, these pods need to be restarted to calibrate on vertical scaling. Vertical scaling is a little bit different than horizontal scaling. We're going to focus a little less on vertical scaling today. We'll talk about it a little bit more later, but we're going to focus on that first type of scaling today, the horizontal pod scaling. And when we talk about horizontal pod scaling, we want to talk about what we call Tetris scaling challenges. So how we align pod scaling with infrastructure scaling and how the game of Tetris needs to be played. There are a few types of mismatches where the Tetris game doesn't line up. And these are what we need to take into account when we look for inefficiencies inside a Kubernetes cluster. So this first mismatch is when a pod needs to be scheduled by Kubernetes. Let's say this pod coming in on the right with 3 vCPU and 4 gigs of memory. And there's space, total space in the cluster. There's 3 vCPUs of space in this cluster to schedule this pod, but not on one node. So Kubernetes is not going to schedule this pod. There's no way to run it because a pod needs to run completely on a single node. Because there's no single node to meet this requirements, this pod will stay unscheduled, unfortunately. And it will remain there until the right infrastructure is provided to the cluster. Now, let's say we bring that same node to a cluster that's not fully provisioned with infrastructure yet and has 3 vCPU and 4 gigs of memory, but we bring the wrong instance type. Well, we end up with the same problem. It's still pending. So we've tried to make our infrastructure efficient by adding many different types of infrastructure so we can have our many different types of pods land on different infrastructure within the Kubernetes cluster. But we don't have the right type of infrastructure, the right type of VMs, and the right type of instances for this new pending pod. So it's going to stay unscheduled. Third, on a scale down, what we will see is eventually our infrastructure will be over provisioned. Our applications are scaling down, whether it's nighttime or off hours, and we're running too much infrastructure. We're spending too much money. So we need to take infrastructure away. When this happens, we notice that there's a lot of empty space. We need to get rid of that empty space. So we drop a server from the cluster. Now, unfortunately, dropping this server from the cluster has left a particular pod that needs 3 vCPUs. Now, there aren't 3 vCPUs left on any of the nodes that remain in the cluster. Therefore, this pod now goes from running to unscheduled, which is very bad. In this scenario, it would have been better to take away the M5 large or the C5 large because the pods on there could have been rescheduled on a different node in the cluster, and we could have remained efficient with the cluster and still run all of the pods that we needed to run. So with this in mind, understanding the different types of mismatches that can happen between pod scaling and infrastructure scaling, what type of approach do we need to take to Kubernetes running in the cloud? And the bottom line is we need to stop thinking about nodes and infrastructure. We need to focus on pods, and we need a solution that will bring the infrastructure for us so we don't have to think about it. So when containers are first-class citizens, the instance size, type, pricing, it should all be determined by the pods and the containers. It should honor any labels, taints, tolerations, network, and storage requirements. And those should all be applied to the pod or the container and not to the infrastructure. The infrastructure should be provisioned to match what the pod needs. So if we have pending pods that need 1 vCPU or 10 vCPUs, or we have pods that need a GPU or pods that require on demand, those characteristics should define how the infrastructure gets provisioned and not the other way around. We should not think of it that we provision infrastructure and then deploy pods. We need to change the way that we think. We need to say we deploy pods with specific characteristics, and because of those characteristics, we get the infrastructure that we deserve. So how do we achieve this serverless or nodeless experience? We really need to drive towards no management of the underlying infrastructure. We focus on pods, deployments focus on pods, infrastructure comes to meet those characteristics. Scaling by request and real-time requirements. As pods scale, infrastructure needs to scale, and it needs to scale correctly. Utility building, we should only ever pay what we use for. We should be able to scale up to 1,000 nodes or 1,000 pods, and we should be able to scale down to 0. And infrastructure should be able to follow those requests. Also, scaling should be fast. There should be enough infrastructure that whenever there's a burst in scaling needs for a pod, that those demands are met, and that pods aren't waiting long periods of time for the correct infrastructure to be available. So let's dive into some numbers. So for one example, we have a pod with 6,500 megs of memory and 1.5 vCPUs, and then we need to scale that pod in a few different ways. Now, we could go out and just get the cheapest instance available, which would be an M5 large, and we just scale that for as many pods as we need. That would actually be the most expensive way to go and do it, though. Because of how the pod is, the characteristics of the memory and the vCPU, as this pod scales, it's actually more efficient to use larger instance types. We can drive more cost savings, and we have the on-demand hourly cost here of what this pod would cost on these different instance sizes of the M5 family. And if you know this pod is going to scale, it's actually cheaper to use bigger instances and not the cheaper, smaller instances. So this is just one example of how choosing the right instance size within a family can save you money based on the scaling requirements of a pod. In our second example, we're going to show 6,500 megs of memory with 1.8 vCPUs and show how different families themselves can show big differences in the price. So the difference between a C5 extra large and an M5 extra large, for this particular pod, as it scales, it's much more efficient to run this on a M5 extra large. You're going to see bigger gains in cost, and you're going to see more allocation per CPU. So let's talk a little bit about Ocean by Spot. This is what we really want to drive towards in this conversation, which is how we view the world of nodeless autoscaling. We want serverless containers. We don't want people to think about servers anymore. We want that pushed to the background. We want customers to be able to deploy containers on abstracted infrastructure and save up to 90% in cost reduction. What do we mean by that? It's not only the use of spot instances, which are the excess capacity of the different cloud providers like AWS, Azure, and Google. They all sell capacity at cheaper rates. The spot market is able to provide instances at a fraction of the cost, with the caveat that the cloud providers can take those instances back at any given time. But with container-driven auto-scaling, we can also more efficiently pack pods in to specific instance types and not only save money with the spot instances themselves and the different markets where you can go buy compute, but also in the efficiency of packing pods and bin packing pods in on the infrastructure, in on the instances themselves. So we can save on the instances by buying them on these spot markets from the cloud providers, and then we can also save by running them as efficiently as possible within the Kubernetes cluster itself. Now, when you're generating these savings from the excess capacity markets of the cloud providers, Prediction is key. These instances can be taken away from you at any given time. And Spot, Ocean by Spot, is always watching these different markets and predicting when these markets are going to be at capacity or be taken away. Anytime Ocean knows infrastructure is going to be taken away, let's say 10 VMs are going to be taken away because they're going to be reclaimed by the cloud provider, Ocean will scale up the right amount of instances to cover the pods before those instances are taken away. So we can gracefully move pods from the instances that will go away to more sustainable instances that we found in different markets and keep the applications up and running. And this is part of the SLA that Ocean by Spot provides to ensure you that you'll always have the infrastructure to run the applications running on the most cost-efficient VMs that you can find on any cloud. Ocean works with any control plane. Ocean's not very concerned with the master control plane that you're running. It doesn't look to manage the master control plane. It integrates seamlessly with the control plane while managing all the workers. Again, if we look at the two different planes, and we'll go to the next slide, if we look at that control plane and we look at that data plane, the control plane can really be anything. It can be EKS, GKE, AKS, it can be any Kubernetes, and even outside of Kubernetes, it can be Docker Swarm or Amazon ECS. Any type of container orchestrator can work with Ocean, and then Ocean will take care of scaling the worker nodes, scaling that data plane, bringing the right infrastructure, the right storage, the right network, the right worker nodes to the cluster so pods can always be scheduled and always be run. Another point that I touched on earlier that I want to expand on now is running workloads immediately. So when we scale, we don't only want to get more infrastructure, but if we scale a lot, we want a little bit of that infrastructure to already be available because we don't want the next pod to always be waiting on a new VM to be provisioned. Now, there's a few different ways to do this. There's over-provisioning, which is the easiest way, just provision a lot more infrastructure. Now, this, of course, takes away any cost savings that you would have gotten through running an efficient cluster because you're just running more and more infrastructure than you actually need. And the idle, you're going to pay for all those idle resources. The second is pod priority. You can run a fixed amount of infrastructure and then give priority to pods. So higher priority pods will kick out low priority pods. This way, the higher priority work gets done, but you're always sacrificing some work for other work. And then the last one is adjustable headroom. You can actually configure headroom in a variety of different ways. There's different design patterns on how to do it. The most efficient way is to combine characteristics together of the applications that you have running in your Kubernetes cluster. So if you have a bunch of different applications, but they all share a common underlying characteristics, they all use the same type of CPU, or they use a similar amount of memory, or they kind of have the same shape and size to them, you can intelligently provision headroom based on the aggregated characteristics of these pods. So when any one of these applications scale, it's always likely that they will land on infrastructure that already exists. And as they land on that infrastructure, it is automatically scaling in the background to make sure that capacity and headroom stay in front of any scaling that's actually happening with the applications. This is the pattern that Ocean provides. This is what Ocean does. Ocean takes a look at everything that is running in a Kubernetes cluster, configures a certain amount of headroom for those applications based on common characteristics, and ensures that pods always have a place to land when they need to scale. Along with managing headroom and keeping intelligent and cost-effective ways for that next pod to always have a place to scale, Ocean also shows cost management and showback to a granular level of the pod. So as big as a namespace or as big as a cluster, down to a namespace and as small as a pod, you can get cost and showback information for everything running in your Kubernetes cluster. Ocean itself also offers a vertical container auto-scaling solution. This is a replacement to the standard vertical pod scaling solution that we talked about earlier in the presentation. In Ocean, we take longer metrics histories of everything that's running. We also account for not only vertical but horizontal scaling of the pods. And we'll hook into any CI/CD system that you have through our RESTful API or through integrations with Terraform or Jenkins or other CI/CD tools that you have, so that you can automatically apply these recommendations every time you deploy your application. This way, you can take the guesswork out of developers or engineers thinking about how much CPU and memory they need, and have the system actually tell you how much vCPU and memory you need to run an application. And lastly, I touched on this just before, or not lastly, but I touched on this just before, infrastructure as code. With infrastructure as code, you can deploy everything Kubernetes with the DevOps stacks that you're using today, whether that's Terraform, COPS, EKS CTL. Ocean integrates very seamlessly with the tools that are at your fingertips today. Furthermore, we're officially part of the EKS Workshop from AWS. If you use AWS today and you use EKS, we'll share this link for the EKS Workshop. Ocean is an official section of this workshop for a turnkey solution that will run your EKS cluster as efficiently as possible. Again, this workshop comes directly from AWS. Ocean is a part of this workshop. So without further ado, let's actually get to a demo to see what we can do with EKS specifically for this demo and Ocean. What we're going to do in this demo is we're going to launch an EKS cluster with EKS CTL, much like we do in the workshop. We're going to launch this cluster, and then we're going to see that Ocean is automatically provisioned and everything's set up for us. We're going to install the metrics server, and the horizontal pod autoscaler is going to already be provided by the cluster. We're going to deploy a sample application, and then we're going to drive a ton of traffic. We're going to have the horizontal pod autoscaler scale that application up, but only the pods. We're going to see that the pods, in turn, demand that more infrastructure be provisioned. Ocean's going to take care of that for us, going out into different markets and finding different VM sizes to bring to the cluster to fulfill the load. And then we're going to cut the load, and we're going to bring it back to zero, and we're going to watch everything scale back down to its original state. Now, a lot of these tools take a long time to provision, so we pre-recorded this. I'm going to talk over it now. But so we don't have to sit here for 10 minutes of a EKS cluster provisioning or wait for instances to pop up in lieu of time. We'll talk through what's actually happening in this demo. So the first step is to run EKS CTL with all default parameters and the Spot integration. So the Spot integration is going to integrate Ocean right in EKS CTL. It's going to provision the whole cluster using CloudFormation on the AWS side. And once that's done, we're going to have a Kubernetes cluster that's up and running. If we do get services, we're going to see Kubernetes is running. And then we're going to look at the deployments. And when we look at the deployments, we're going to wait for core DNS and our Spot controller to be up and running. We wait a couple minutes, everything's up and running. Now we're ready to go look at our cluster. If we go to the Spot console, we're going to see that EKS CTL provisioned not only EKS, but also Ocean, deployed our controller, and we can visually see everything that's going on with our Kubernetes cluster from one location. Now, it's not too exciting just yet. We only have one node in this cluster, and if we go take a look, it's running the default pods that come with EKS. We have core DNS, we have a kube proxy, and we have our controller running. This is the bare minimum for a controller or for a Kubernetes cluster. So let's go back to our command line and let's start thinking about how we can scale this up a bit. So we're going to install the metrics server, pretty standard install right from AWS's website. We're going to install a sample application that we're not going to get too deep into right now, but it's a echo server. It basically echoes back any request that's sent to it. We're going to check that it's up and running and deployed. It comes with a service and a horizontal pod autoscaler. We're going to see the autoscaler is just getting up and running. It hasn't yet gotten all the metrics that we need to scale this deployment yet. and that we also have a service. Under this service, we get an external ingress, as I talked about before, to the cluster. This happens to be an AWS Elastic Load Balancer. We're going to copy that DNS name because we're going to use that DNS to fire up a bunch of attack nodes to drive traffic to our sample service. If we take a look at the state of our cluster right now, we can see that we have one Echo server running, and we can go ahead and test this Echo server just to make sure that it's working. It's only one pod. We can't send a ton of load to it right now. But if we do a curl against that DNS name for the load balancer, you'll see that we get back the request that we sent, and it also tells us the container that served the request. And now if we take a look at the HPA, it's actually gaining statistics about our deployment. So let's fire up some traffic. What we're going to do is we're going to use another product by Spot called Elastigroup. You can think of Elastigroup as an auto-scaling group, but optimized to run on top of Spot instances in excess capacity. We're going to set some user data for some straight up VMs, no containers here. We're going to find some good markets to run our Spot instances in. We're going to pick 5 different availability zones to choose from. And we're going to edit the user data to have the DNS name of the service that we created in Kubernetes. We're going to use a program called Vegeta that is going to fire off 1,000 requests per second per instance that we use. Now, right now, the Elastigroup has 0 instances. So initially, we're going to scale this to 4 instances. We have none running right now. We'll go up to Actions, Manage Capacity, and we're going to change target to 4. So this will be a total of 4,000 requests per second that we will be firing off to our test service that is running in our EKS cluster. Once these servers are up and running, we can check on our Kubernetes cluster, and we can take a look at HPA, and we can see that we're up to 250% of CPU. Hey, let's go check on our nodes. Let's see what's happening. So we go back to our Spot console. We're going to take a look at our nodes, and we see only 1 instance is running. Let's hit the refresh button. Still only 1 instance is running. What's going on? I thought this thing was supposed to scale. Let's go back. 4 replicas. So HPA had not yet decided that we needed enough replicas that infrastructure needed to scale up. So if we wait a minute, and just about a minute, we'll see that the HPA has now decided that 25 replicas need to be made of this pod. So let's go back real quick to the Spot console. We'll do a refresh, and we'll see now there are 2 nodes registered with our cluster instead of just the 1, and that we're scaling up the number of pods that we need to serve from the 7 that were there before to 33 that are being served by our cluster now. So let's check again on the HPA. We see that the target CPU is dropping closer and closer to our 10% threshold. So we need to fire more attackers at this because the HPA is not going to scale up past the number of nodes that we currently have. So let's change the number of attackers we have from 4 to 8. That'll change the number of requests from 4,000 per second to 8,000 per second. And we'll see what happens with the HPA and the scaling of our little Echo server that is running. We have the instances up and running. We'll go back to the HPA, and we'll see that HPA now wants 70 replicas to handle the increased load, the instant increased load that we've seen. So with 70 replicas, we should be able to go back to our Ocean cluster and see that the infrastructure is matching what the pods need to execute. And if we refresh, we'll see here that we're now up to 5 workers. And those 5 workers are handling all those 70 pods. And this is just a warning that this one instance is happening to get close to the maximum number of pods that it's allowed to run. We're completely healthy. And then from our main page, we can see all the pending pods, running pods, unscheduled pods, the different instance types we're using, and the allocation of how efficient that we're being in our cluster. The HPA has gone all the way up to 100 replicas, and our CPU target has gone down to 8%, which is below our 10% threshold, which means now we either have to launch more nodes or we can end this little experiment. We're going to choose to end this experiment, and we're going to go down to 0 attackers. Now that we have no attackers running, or once all the attackers are terminated, HPA will realize that there's no traffic coming into the pods and will start scaling pods back down to 0. So we have no pods running. Our cluster is healthy. It still has 6 nodes. We're going to go back in and we're going to take a look at the HPA. Now, again, if you remember from earlier in our presentation, the horizontal pod autoscaler is not instant. It doesn't like to flap up and down very quickly. So it's going to take metrics over a period of time. So the first time we run this, we're actually still going to see that we're still about 8% CPU. We're still about 100 replicas. Even when CPU drops to 0%, we're still about 100 replicas. We're going to have to wait a few minutes before the HPA really decides that it needs to scale back down to 1 pod. Finally, we'll see that CPU is at 0%, replicas are at 1. We'll be able to go back to our Kubernetes cluster, take a look in our Spot console that in fact, all of the pods have been removed and scaled down. So Ocean will act accordingly and start intelligently taking the right nodes out. You'll notice it's taking the nodes out with the least amount of pods on them. It's making sure the least amount of pods get rescheduled in the system. And we're back down to just that single instance that we started with when we provisioned the cluster in the first place. So that's the end of the demo. And what I really want to drive home here is that all we did is launch a Kubernetes cluster and start scheduling pods. We never defined a VM type, a VM size, infrastructure, storage, networking. We didn't define any of that. We used the defaults from EKS. That provision not only EKS, but Ocean by Spot. Together, these tools made it very easy for us to take a pod-driven application, scale it up, then scale it down, have everything work as anticipated. And if we wanted to, we could take that and configure it for any situation that we want. It doesn't have to be the default setting. You can go into EKS CTL and not only set all the little bits and bytes of EKS and Kubernetes, but you can also set all the bits and bytes of Ocean by Spot, and you can tell it how many launch configurations you want, the different types of storage, different types of network, subnetworks, anything that you want, you can configure. You can put your own guardrails on this, and Ocean will scale in the most efficiently way possible with that information. So I think everybody should want to try out nodeless or serverless Kubernetes clusters. I'll appreciate any questions anybody has from this presentation along the way, either about Kubernetes, about Ocean, or about the combination of the two. I'm Kevin McGrath, CTO of Spot, and I thank everybody for listening and watching this demo.